recording has started. I switch off my camera and mute.
Okay, so hello everyone. I'm Alessandro, chair of the Linux Feature for Safety Critical System Working Group, and this is the annual SIG for my working group. So, what is LFSCS as we call it? In simple terms, we look at Linux and we ask difficult question. Not does it work? We already know it works. The real question is, how could it fail, especially inside a safety system? Our mandate is to analyze Linux feature in the kernel, and when needed, also in user space, and understand where safety assumption may break. We look at topics like memory isolation, allocation behavior, and process boundary, areas where failure could have a safety impact. We do not certify systems, and we do not build safety case. Our role is investigate, identify risk, we frame scenarios, and we turn them into reproducible questions for the broader ecosystem. So, why does this working group exist structurally inside the ELISA? LFSCS is what ELISA calls an horizontal working group. This means basically that we don't belong on a single domain. We operate across all of them. Alongside us, there are other horizontal working groups like the architecture, the tools, and the OSEP. Each of them focuses on different technical concern. Then we have the vertical working group like automotive, aerospace, medical, and the space grade. This vertical working group brings real development use cases and safety requirements from their industries. So the work models work like this. Vertical group tell us, here's what safety system needs. And we look at Linux and ask, which feature could make those requirements difficult to achieve? In this way, we translate domain expectation into technical investigation, often down to kernel behavior, feature design, or system interaction. To keep progress moving, even when vertical timeline differs, LFSCS focus on fundamental safety primitives, which we'll look at in a moment. In practice, we're building a reference foundation that vertical working group can later adopt and stress test. So, this slide essentially is an overview of what we've been investigating during this cycle. The topics were not chosen randomly, but they also did come from a strict top-down roadmap. So we came from emerging opportunities, other from member interest, but all of them were framed under the same mandate: identify where Linux safety system assumption may fail. One area was the minimal Linux footprint, as Philip suggested earlier. This builds on earlier minimal config work, looking at which features are truly required to run on a real application. This helps us understand not only how to reproduce a system surface, but also which kernel features are most likely to be exercised in safety deployments. And in a safety system, reducing exposure is often a good start point. The second and probably deepest investigation we focus on is the virtual memory areas. VMA are one of the kernel core isolation mechanism and also one of its most complex subsystems. So naturally, they are coming a critical place to study when trying to understand where isolation assumption might be stressed. Memory management in general offers many concerns, which make it especially relevant for safety systems. We also had some member-driven exploratory topics. These were not a primary work stream, but forward-looking discussion sparked by contributor interest and expertise. They show how the group can remain flexible and responsive when safety questions begin to emerge. Now, let me focus on one example investigation, the minimal Linux. The starting question was simple. If you want to deploy a Linux in a safety system, what is the smallest functional system you really need? This work builds on earlier minimal config studies, but instead of only reducing the kernel option, we look at real application behavior. We traced execution path, we observed which kernel features were actually used, and we mapped the essential system interaction. One important aspect of this investigation is that it does not depend on a specific domain use case. Understanding the minimal runtime surface is a foundational work, useful whether you are targeting an automotive ECU or a satellite controller. In the QR code, you can find the document produced by the working group as an outcome of that investigation. This kind of work allows us to stay productive even when domain requirements are still evolving. It helps us build analytical baselines so that when concrete safety requirements arrive, we already understand the feature surface involved. Reducing the footprint helps limit the system exposure, of course, but it does not tell us how strong isolation is inside the system. And that is what led us into the deeper investigation around virtual memory areas. So, the second and probably deepest investigation focused on memory isolation, specifically on virtual memory areas. If the minimal Linux work help us understand system footprint, VMA analysis help us understand isolation guarantees. VMAs are Linux main mechanism for context and process level separation. They control how memory is allocated, mapped, and protected across address spaces. So, when evaluating Linux in mixed criticality system, this subsystem that must be clearly understood. And importantly, this investigation is not tied to a specific domain. Wherever the system is automotive, aerospace, or medical, memory isolation remain foundational. On this slide, you can see how we structure this work. You can think of a bit like a Jira epic, where the VMA representation sits at the center, and around it we opened a lot of very detailed investigation tickets. Each deep dive looks at a specific aspect: life cycle behavior, mapping evolution, allocator interaction, pressure handling, fault paths, and so on. Some tickets were small, some other keep expanding, as JIRAs usually do. Together, they help understand isolation, not as a single mechanism, but as a system of interacting behavior. So we analyzed how VMA are created and destroyed, how mappings evolve over the time, and how the subsystem behaves under stress condition. Memory management contains many corner cases, which make it especially relevant for safety analysis. The goal was not find bugs, if found are welcome, but we aim to understand where architectural flexibility might conflict with deterministic safety expectation. The QR code link to the work in progress document we are doing, and an early working presentation delivered at Munich workshop. So, spatial isolation topic originated within our investigation, where linear map interference was identified as a potential isolation concern and discussed at workshop level. One aspect we are starting to observe is that mitigation ideas related to it are beginning to emerge more broadly across the ecosystem. Early work mitigation thinking explored approaches leveraging the old 32-bit system HIMEM mechanism. However, the upstream landscape is evolving, and with the HIMEM now moving toward deprecation and probably eventual phase out. In parallel, other related mitigation ideas have begun surfacing from the wider community, and work in this space is expected to be openly published. As this development intersect with our investigation underway, the working group is tracking them to understand how they relate to the isolation question we have been studying. Behind that investigation, aligned signals, we also had a few member-driven exploratory discussion. One example looked at the pointer safety models, including concepts explored in projects like Cherry and FieldC, where metadata can be embedded within pointers. This was not a core workstream, but it generated a useful discussion, both inside the group and across the broader community. It showed how community-driven topics are not only welcome, they are actively considered within the working group, and they help extend safety discussion to audience who may not be directly involved in the safety engineering. So, what has this work translated into so far? First, at its core, investigative output. We have been analyzing Linux feature through the safety lens, mapping potential failure mode, and identify where assumption may need stronger guarantees. This work doesn't remain inside the meetings. We share it through public discussion, documentation, and workshop. So the analysis become visible and reusable. Our investigation have also highlighted how important collaboration with horizontal group is, particularly when analytical findings need execution pathways. For example, when we identify interesting fault scenario, this can be fed into tooling exploration, where hypotheses can be turned into reproducible experiment. Execution through tooling remains an important objective, and expanding this path will depend on restoring sustainable capacity in the tool working group. This investigation tooling pipeline become more important as our work matures. And finally, we continue to keep space for member-driven exploration, ensuring that emerging safety topic can enter the discussion even outside formal work stream. So this is your opportunity to get involved. Our working group is meeting on Tuesday at 1300 chat or chest, depending on the summertime. You can join the main list, which is something we use to communicate somehow, or join the Discord, more recent and practical way to interact. Then you can surely participate in the GitHub work, which here is a link. And there is the annual update for my working group. Thank you for attending. If any question, please feel free to ask.
Thanks, Alessandro. And I guess we can also use the time to ask other questions. So if there's something from the previous sessions, we're hopefully able to answer a bunch of them. So you don't have to limit it to this session alone.
I'm going to stop the recording then.